Hello, everybody. It's a great honor for me to introduce to you Professor YangQuan Cheng, who received his PhD from Singapore University. He joined faculty of electrical engineering in Utah in 2000, and currently he is professor at the School of Engineering at University of California, Merced, since summer 2012. He's teaching a lot of different topics and participating in more journals than I can read. But I looked up his age factor. It's 91. In Google Scholar, you find that. It's pretty hard to keep track of that. And with that, he's listed as highly cited researcher by Claviet in 2018. YangQuan, it's an honor to give you the floor. You're going to talk about fractional order motion control as an overview.
Thank you. Thank you, Peter, for your introduction. Thank you very much. So allow me to, share. Yeah, now I can share. Yes. Okay, so I have been revising my slide. I didn't get enough time to prepare the dream talk I wanted to prepare. So welcome to my talk. So basically, this talk is centered around a book with the same title, Fractional Order Motion Control. But that's a very old book, so it's not very interesting. Actually, what I wanted to talk is this title, but I don't have enough time to do it. You guys heard of Metaverse recently, right? So from Facebook, they are changing their name to a Metaverse, okay, Meta. I think putting Meta with mechatronics makes very good sense. Let's think about it. Next year, if I were invited, I'm going to use this title. All right, so let me thank our organizers and thank University of Luxembourg's Professor Peter there and Flapper group. Thank you for all your efforts. Appreciate that. Thank you all for coming to my talk. So I'm from University of California, Merced. We are the number 10 campus in the University of California system, centered in the Central Valley. The Central Valley basically is the third world country. It's majority of those are low-income agriculture population. So that's why they put a research university there to transform the whole society. It works so far. Our university started in 2005. Just for your information, we got 2 Nobel Prize in the UC system again this year. Last year, 2. So far, got 70 total. Our ranking in the public university is number 38 this year. Last year was 40. And our ranking on the overall US is number 93. Last year was 97. We're already top 100 university in the United States. If you check all the younger universities, we're number 3. I'm going to mention carbon neutrality again later, give you an update about our campus. So my lab is basically a mechatronics lab. Okay, so that's why today here. But I also do fractional calculus. So these two, they are connected. And today I'm going to give you a small taste of how they are connected, why that's an important connection. So let me move on. So basically my lab is called a drone lab. Drone is a mechatronics device system. So there's no strange here. And for drone applications, we use for precision ag and environmental monitoring from like water, fire, soil, dust, air quality, and so on and so forth. We're working with different partners. So 3 updates. So carbon neutrality. December last year, we already declared like we reached carbon neutrality. It's our first public university announcing that. Everybody now is working towards this goal. This summer, we got $20 million from a person named Mackenzie Scott. Her husband is the owner of, her former husband is the owner of Amazon. You probably heard about that story. So remarkably, she donated $2.74 billion for 286 organizations. So we are one of these 286, 20 millions. And just a few weeks ago, it was announced that we're going to get a new medical school. Usually it's very expensive. The state of California committed to do that. So it's great. Our university will have a new face. So welcome to visit us. So let me start by saying that mechatronics has a broader meaning. Just give you an idea, if you combine a human in the loop, then you will see a lot of biomechatronics. So how to control the biomechatronics, make the mechatronic system to understand your real needs and work together in a synergistic way. You need advanced controls plus fractional calculus. The reason is your arm made by your neuromuscular system is basically infinite dimensional system. It's mostly a fractional order system as well. Therefore, to have a natural, realistic motion, you need to use fractional order control ideas so that it's not like a robotic motion. It's a human-like motion. I'm not going to elaborate on that, but here's the dream topic I'm going to talk next time about meta-mechatronics. I put this together. Nobody put this one on the Google yet. So let's try to create something. So when Zuckerberg mentioned about the meta universe, I suddenly realized that the foundation is actually our mechatronics, controls, all those foundations. And now we are talking about fractional order controls. I see all these connections. Therefore, I want to say, that meta-mechatronics is a trend. It's a mega trend. So you can imagine that you watch this in the movie, Avatar, and so on and so forth. You need natural motion. You need fractional calculus. Okay. The same thing here, like you have rehabilitation devices with you. So the human and the mechatronic system, they combine, merge in together as a single entity. So then we can say this is a meta-mechatronics. The same thing like a metaverse. Okay. So I want to remind everybody that mechatronics, how they combine with fractional calculus, that question was asked more than 10 years ago. And in 2013, in the Journal of Mechatronics, we had a special issue here about fractional calculus combined with mechatronics controls. There's a special issue, you can check it out, 2013, Mechatronics Journal. Later on, I also did several special issues on the journal called IEEE/CAA, Chinese Automation Association. It's called JAS, Journal of Automatic Control. We had like more than 50 papers accepted from over 100 submissions. Then International Journal of Control, we had dedicated a special issue in 2017, 4 years ago, about fractional calculus modeling, analysis, and design of control systems. Just to refresh your memory. So it's a very nice special issue collection in the National Journal of Control. The ISA transaction, we had also a special issue on fractional order signal systems and controls. That's in 2018. So when we say fractional order calculus, mechatronics, I feel like they are naturally should be combined together and applied together. So in fact, I heard last last plenary speaker, talking about complex order. So yeah, of course, I know that very well, that project background very well. So I'm very pleased to see different people meet with fractional calculus as background. So we maintain a book of fractional calculus. So please, if you want to check out FC books, so we update from time to time. And so with that, I want to remind you that there are many other special issues like Asian general control, like applied abstract analysis, this is a philosophic transaction of a Royal Society Part A. This is a prestigious one in 2003 with 2013, yeah, 2013 with Professor Kurt Jürgen and Champing Li. So we have many other special issues like mathematics problems in engineering, International Journal of Differential Equation. So all these are special issues. Just a reminder, it's a very active area using fractional calculus in real world problems, not just electronics. I want to mention one more thing here. Number 4, philosophic transaction. This is a very interesting journal, has a rich history. When Isaac Newton published the papers on this journal, and like Kelvin for the thermodynamics. Okay, so basically I told you that I'm going to give you a tour, not tutorial, in fact, it's a tour. I'm a kind of tour guy about this fractional order motion controls. Everybody knows that the control has broadly 2 areas. One is motion control related to motion governed by Newton's second law. Another one is regarding process control. That is usually by the heat or temperature, which is governed by parabolic partial differential equations, infinite dimensional. But we focus on the motion control. But on the other hand, in the motion control, we have motors and we don't see Maxwell's equations. So the idea is we're now treating it as a lumped parameter systems and usually in the integer order. So there are lots of approximations you can see. So that's why there is a room for fractional order control to play to further improve the performance. Make sense? So this book is end of December. I moved from Utah State University to UC Merced in summer 2012. So I'm in my 10th year in the new university. The new university is 16 years old. So I feel very happy to apply fractional calculus, and I even have a fractional calculus, fractional order mechanics dedicated course offered in UC Merced. So basically give you a tour. We have several parts. The first is regarding some fundamentals for fractional order controls. Then after that, we talk about how to use fractional order controller in velocity servo. So basically how to control a reference is the velocity. Then part 3 is a position servo. Part 4 will be a stability and feasibility for fractional order PID design. So I also see the last plenary speaker showed the stability domain. So beyond the domain, then it is not stable. So to know the stability map is very important. So we discussed that problem in part 4. We call this achievable design space. Okay. Part 5 is regarding a disturbance compensation, like a disturbance observer in the fractional order sense, why we need this, and how this can be further improved improve the integer order case. And of course, we have AFC, called adaptive feed-forward cancellation of non-periodic disturbances. Okay, so we did the fractional order modification to that, so we'll be able to tune like the depths of the notch filter. It's amazingly interesting. And cogging is also a periodical effect in the motion control. How to compensate that? We use a fractional order case on that. So, but remind you that cogging effect is a periodical effect, but the periodicity is not with respect to time. It is periodicity with respect to the angular displacement. Okay, so that's different, not time periodic, it's state periodic. Chapter 16 is periodic. So based on that, we'll talk about periodic adaptive learning compensation idea. Okay, it's similar to repetitive control. Part 6 is regarding nonlinearity, how the fractional calculus based methods can be used to handle those nonlinearities. So like you have electric shaft, you have a very low speed position servo, then those those nonlinearities like data zone, like hysteresis, backlash. So how fractional calculus idea could further reduce the effect of those mechanical nonlinearities with memory. I think chapter 19 is most interesting to me. I also saw similar ideas regarding conditional integrator, meaning you have some logics built into the integration, and that the integrator could be a fractional order, and there are some optimal tuning opportunities for those conditional integration. So this paper published in the JPC is so far one of the best papers I feel proud of. So last, we have 2 chapters on 2 real systems, and we tested on the real systems. The first one is a fixed wing UAV. We flew fixed UAV using fractional order control for lateral directional control. We flew that with test flight, logged test flight results. This was published in Control Engineering Practice, still widely cited. It is the ever first paper. I can say we were perhaps we are the first to flew fractional calculus, to fly fractional calculus. Okay. So last is regarding hard disk drive servo system. As previous presenter talked about wafer. So this is a very high ultra precision system. So there are a lot of important advanced control ideas should be used in that kind of system. So I worked in Seagate for 18 months. So I can fully appreciate that effort. It's very, very cool. It's enabler. I saw the word he used, the previous speaker used. It's enabler, meaning if you don't have this advanced idea, then the whole thing will not work as you wished. So then you will see fractional order idea can further improve. Okay, further improve. So that's the overview of the whole book. And let me see. So then I can go over and over, and you can see I have about 250 slides. So you don't want me to go through every chapter. So I will see whether we can finish the part 1, okay? Part 2 regarding velocity servo, some basic ideas, okay? Give me a signal when time is up. I think I have another maybe 15 minutes, 20 minutes, okay. Okay, so I assume I have 20 minutes. So I skip that. I don't want to tell you the contributions. So got a feeling here. You can use fractional calculus whenever you see a motor. So why this is possible? So I keep asking people, they feel, I never thought about it. So this is an electromechanic system. We have electromagnetics as a field in there, right? So why you don't see a Maxwell equation? Okay, where is the Maxwell equation? You don't see Maxwell's equation, right? So we use a lumped parameter thinking to model the whole system. But in a very high precision, you have to consider all those high frequency resonances. You have to deal with them. In that case, fractional calculus definitely will be able to help. Okay, so this part for fractional order control of velocity servo problem is just give you a taste of fractional order motion control. The book covers more wide topics, so you can check it. So I'm going to go through very brief tutorials on here. So we set up some of the resources for fractional calculus under our, I checked this is still working. So just for your information, I maintain a rich collection of fractional calculus research resources. The most important books, the more books I already showed you here. Most important two books for beginners are, one is Igor Podolomy's fractional differential equation. The chapter 10 in this book has very rich collections of applications, engineering applications. So this is the first book to have such collection of applications to further convince people this is not just a mathematical game. This is very useful. So in the next few minutes, I'm going to show you some real enhancement for the control, for the velocity servo. Another book, very accessible, is by Richard Megan. Although he focused more on the bioengineering, however, it is also useful for any subject area in engineering. Okay, so how this one happened? So this is, everybody have, maybe many of you have seen this one for many times from my talk before. Let me remind you why L'Hopital can ask this question. Okay, what is the enabler for L'Hopital ask question for Leibniz? The enabler is the Leibniz idea to use this symbol so that you see the n in here, you will be asked, what if n is half? Do you remember Newton's symbol? His notation is f dot, right? You cut one dot, you get two dots, not half, okay? So notation matters. Definition, I think many of you here perhaps know this. So the starting point perhaps is the Cauchy integral formula in integer order case. Then extend this one into fractional order case is straightforward by replacing the factorial into a gamma function. So you get this. This is a binomial expansion for fractional order power using an approximation of finite difference. So this is also standard definition here. We don't have to go in depth here. So the Riemann-Roulio, it's a convolution. Okay, this is a convolution structure. So this is a power law memory kernel. So this is a Riemann-Roulio integration. Okay, then Caputo is here. Okay, you do a differentiation, then you do integer order differentiation first. Then you convolute with inverse power law kernel, then you get Caputo. I want to mention that Caputo derivative here is anti-intuition because the reason we use Riemann-Roulio fractional order derivative is because f is very ugly, very bad behaved. So we cannot handle it very well in integer order case, like a Weierstrass function is nowhere differentiable. So then capital derivative does not exist for that. But however, Riemann-Leibniz derivatives will be. Anyway, in the system level, so you simply say, oh, whether s to the power of alpha or alpha is not integer possible? Yeah, possible. Mathematically, even in MATLAB, you can do the same. So you can write a Laplace transform. Of course, we assume zero initial conditions here. Then you can write this type of general fractional order differential equation, linear time invariant. So this format can be actually put into MATLAB by a famous MATLAB toolbox developed by Professor Xue. It's called FOTF, fractional order transfer function tool. You're just using like a TF transfer function tool in MATLAB. You can input this model in there. Then you can do anything like you do a regular transfer function. It's amazingly efficient. So try out books. So there are many other definitions like you define from Fourier point of view. So therefore, there's connection of fractional Fourier transformation with fractional calculus, system and controls, signal processing, and so on and so forth. There are rich, like a rich side of fractional order randomness, fractional order random processes. So I'm not going to touch today regarding this. Anyway, using fractional calculus could be potentially more accurate, okay? The stability region is kind of different. 1950, Scott Blair, who is considered as father of rheology, he said it this way. I'm not going to read this one for you. I want to paraphrase for you. So the nature runs in the fractional calculus dynamic way. But our human using integer order calculus to model it and to control it, that's okay. But remember, that's only for your convenience. The nature still runs in the fractional calculus way. Okay, so I think I paraphrase what he said here. Okay, remember that. So nature runs in the fractional order dynamic way. It's okay, we're approximately using integer order, but you should realize that's for your own convenience because you only know integer order calculus. Okay, so therefore, it's important to realize that now it's possible to try, okay? You have nothing to lose. Why? Because you have a potential to beat the best before, okay? You have the potential to be more optimal. You have nothing to lose because the worst case is you are as good as previously you got, okay? But you have potential to be better than the best. So I think that's Richard Megan's idea. This is my student's idea about all this from discrete to continuous tunable. Fractional calculus is like a flexible range, right? So this is obvious, okay? So nature is fractional, but sometimes so close to integer. So it's okay, just say this is integer, okay? Integer order vary. So there are many tutorials resources I put it here. This ACC paper was heavily cited about a tutorial we wrote. Then we have TAC first paper. This is heavily cited. So when people say fractional calculus, fractional order control is not a real control, send us the paper to them. Transactional automatic control, okay? There are already numerous papers showed up in Automatica. So it's real, don't have a bias, okay? Just be open-minded. So stability domain, so traditionally in the middle, so you have stability domain like this, okay? So for fraction order, then you will see the shaded area here. So as if it's like larger, which is interesting. So, but so we usually want this one, this part, stability. But this one reminds you in integer order case, you have a shaded area. This is called D stability domain stability, D-stability analysis. So then if your fraction order is in between 1 and 2, it can be safely converted to this D-stability problem. So it looks trivial. So focus on 0 to 1, okay? Anyway, there are 4 different types. What we learn is only 25% from our textbook, okay? We only learn 25%. But if you consider the disturbance, the noise could be fractional order, disturbance could be fractional order dynamic. So all this add together, you will have maybe times 4. 4 times 4 is 16, okay? I discovered this one. In fact, I tried to talk to the author. This is a US patent, okay? So it's called tilt integration. So you can see this is 1 over n is a real fractional, really fractional. So 1 over n, okay? So this patent discussed. So this is the patent that triggered my interest about, I want to find out what's this. This one leads to me fractional calculus. Then when I did some research, I know 2 important names. One is Igor Podolubny. Another one is Balas Vinagre. So I started to talk to them, and they taught me a lot over the past maybe 20 years. Yeah, 20 plus years already. Amazing. We became very close friends. Very interesting. So what is the TID? He actually borrowed the idea from Bode, Henry Bode. Bode said that PID usually you need to make sure your system this is a body plot, okay? Cross the 0 dB line with desirable rate of decay, okay? So that rate, that one is not multiple of minus 20 dB per decade. So this one is already a fractional order integrator, okay? But however, Bode suggested, so you should roll off properly, and then you have a flat step. So then you do a much aggressive roll off. So having this dashed line is the idea presented in Bode's original book. So you should design your loop in such a way. If your loop does not look like this one, it's not a good design, okay? So there is something you can Google called Bode step design. So how to design this step in here. There's a Bode step toolbox online, you can check it out. This gives you an idea of how to do the specific loop shaping suggested by the Bode. Anyway, I have to tell you that Ken Krong team in University of Bordeaux has a very strong history doing that, suggests ISO damping, frequency templates, all this loop shaping idea. So this is a fractional order PID. So this lambda and delta can be non-integer numbers. So therefore you have more tuning knobs. So then you also can make the lead lag filter with fractional order. So then how to design that? There are some loop shaping ideas. One of the ideas is minimum phase frequency domain fitting, stable fitting for that into integer order case. There are some papers published a long time ago. So that's basic foundation. I'll quickly run through this. I'll finish. So this one shows you you have a control system. You can approximate the very simplest, capture the time constant and gain and delay. That's the first order approximation for any system, right? So we can define a PID control. We have FOPI. So this is 3 different types of controller. I want to make a comparison. Who is working better? So, but remember, the comparison must be fair. So in this case, it's fair in the sense we all have 3 tuning knobs, okay, 3 tuning knobs. So then we will see who can, then optimize everything. Then under the same condition, then we compare. So let's see. We want to put design specifications like phase margin, gain crossover frequency, and at gain, the phase is flat at the gain crossover. So these 3 conditions we add as a constraint, so we can solve these 3 parameters, okay? 3 parameters, analytically even. Of course, numerically is fine. So let's do that. So we can find out, we can achieve this flat phasing here. So flat phase here is my gain crossover. So this design is actually a topic not covered in our textbook. So by having this alignment, so your flat phase, this is a magnet, corresponding to the crossover. So then your system performance will have graceful degradation. So you have a variation up and down for the gain variation. So your phase will get smaller either way, more or less the same. I call it it's a performance degradation in a graceful way. Not like one side is good, another side is very bad. So when you increase the gain or decrease the gain, you have inconsistent performance degradation. Okay, so then you can, what I'm doing, okay. So I skipped this one. So basically, we publish these ideas. Later on, I find out this idea is nothing but is from Bodhi's work. So here, gain crossover, you have flat phase. You will be able to have very robust performance with respect to gain variation. Okay, and this is Bodhi's ideal transfer function. When you cross this one in this domain, so it look like this. Okay. So then you can derive by doing this derivation, you will be able to derive gain phase and flat phase. You can get the 3 equations. You will be able to solve it. So all this can be done automatically. Okay. Okay. All right. So I speed up. Anyway. People are building toolbox to automate this flat face design idea. So something interesting is called, I call bracket PI. So you have integer order PI control. Then you put a bracket, everything becomes fractional power called bracket PI, fractional order bracket PI. So we can do the similar derivation. But you may wonder what is the consequence of doing that. So we also can do, this is a plant to be controlled, it's a fractional order system. We have a background why this is true for a very interesting ion channel gating dynamics. So let me go back a few slides. So we focused on the system like this one, but we changed this one now, or we can rederive. You can do all the way to do many different types derivations using these 3 conditions. So you can design that, you get a flat phase here, but it becomes unstable if you use integer order. Okay, go quickly. So we want to see some results. So this is a step response disturbance rejected with loop gain variation, fractional order versus fractional. This is, yeah. So this is fractional order and fractional order bracket PI. It has much smaller overshoot, better performance. Even you have gain variation 10 plus or minus 10%, still no change of the behavior. So I think I can cover this one, then we finish. Really automatic tuning. How about, I don't have a model of this process, but suppose I can do experiment online, get some oscillation like this, and then we can capture the magnitude and phase, magnitude and the periodicity here how we can tune this controller. So this is practically in process control, but could also be in motion control. When you buy a commercial motion controller, you will see when they start, they do this a few times, they will be able to tune the controller on itself. It's exactly doing this relay experiment, okay? So doing relay experiment. So you can use the same idea to tune on a real system, so it's more reliable. So we tried this idea, and suggest an iterative algorithm, and then we can tune that. So even for integer order and both an integer order and fraction order. So the comparison of the traditional Zaghloul-Nichols versus a flat face constraint. Okay, so that is the idea. That's the idea. So basically here you can see after the tune, the black one is the flat face constraint by using this really automatic tuning tune. So you can see when you have gain variation is more consistent and overshoot is smaller. While this dotted lines, so it's not without flat face constraints, the performance is not as good, not consistent. So for fraction order, we can do the same. So then we did something very similar. Again, you can see some of the fraction order PI and the bracket PI can also be tuned. So these are all highly technical. You need some patience when you derive those phase gain formulas. So I'm going to finish here. Just you know that we have, I can continue for another few hours, but we're running out of time. I just give you a overview and a taste of fraction order control in the motion systems. That the basic message is you can do better than the best under the fair comparison. So with that, I want to stop here so we can have some time for questions and answers. Okay, thank you.
Yeah, thank you very much, YangQuan. Outstanding overview. Thank you very much for that speech. Are there questions from the audience?
I checked the board. There is no questions. Okay.
So I would have a couple of ideas talking about drones, but I'm not sure if this would be.
Yeah.
Oh, I saw questions here.
One or two questions. Just send it here.
Okay, thank you for the questions. I love that. Let me do older ones. Engineering system model as nonlinear differential equation. We have complex responses chaos by how the chaos can be started and exist. The fractional derivatives in the model. This is a very good question. The chaos is inherent system behavior. I believe in the fractional dynamic systems, their chaotic behavior deserve more work, okay, and bifurcation and so on and so forth. Yeah. I'm not in this field. I don't want to suggest any further study. However,
maybe the question is the latest one because the previous questions is to Professor Herder. And how is P controller implemented? Which are the approximations used?
Okay. So here's the answer. Yes, we implemented it. We even flew it. So the idea is how to approximate is to use integer order. Use the integer order transfer function to approximate it. So in a sense that their impulse response are the same, not changed. So this type of method is called impulse response invariant discretization. So you become a digital controller. The code is in the MATLAB Central. You can download a code to do this discretization realization of this one. Thank you for this question. Yeah, we have the code already submitted in MATLAB Central.
Okay.
The last question is, so fractional calculus approximated by the higher order. Yes, it is. So actually, some people, they are not my enemy. So I treat them with sympathy. So they said, you come back to integer order, very high order controller to implement it. So why bother? If you do integer order robust control, you get a high order controller like that as well. Okay, so here's how I respond to them. I said, look, say for example, you have transfer function of 10 over 10, you have 21 coefficients, right? You're including the gain, right? DC gain. So you have 21 tuning knobs, okay, for the 10th order transfer function. But so that's for a robust control, loop shaping, whatever, integer order, so 21 tuning knobs. But in fractional calculus, you may only have one tuning knob. You can discretize in a 10 over 10, 10/10 transfer function. It's also the same number of coefficients, but it's different. Although they are all high order transfer functions, but the tuning knobs, okay, the number of tuning knobs is different. So therefore, fractional calculus should be more welcome by practicing and control engineers. So therefore, all from the tuning knob point of view.
Okay. So thank you, Professor Chen. Yeah, thank you for your answering. Yeah, maybe due to the time limited, so we have to end here, and then give the floor back to maybe Professor Peter.
Yeah, thank you very much, Professor Chen. Thank you much for your